chapter 16, I'm breaking them up. So today we're only going through 15.5, and then Thursday we'll do problems on that stuff, and then we'll finish it up next Tuesday, and then only do problems on that stuff. But I am also going to do some problems as we go through it, because it's easier just to talk about it as we're doing a problem, okay? A lot of this is math heavy, and there's a lot of equations for the next 2 chapters, and they all sound a lot alike. So just continue to figure out ways to be able to identify, and the best way to do this is just randomly to go in the end of your chapter, look at a problem, and say, okay, this is this type of problem, this is the equation I use for it. Like, you don't even have to bother with a pencil and paper, because you guys can all do the math. It's just a matter of determining what you use when and how and where. And if you noticed on that test that you just took, almost every single problem was a variation of one we did in class. In fact, on many of them, I went to the now you try part, and I changed those numbers, and that's the one I did. So keep that in mind. I handpicked the ones in class that I want you to focus on. Okay? Questions? No? All right, good. Okay. We've talked about rate of reaction and different things that affect it and how it goes, and, you know, kind of getting over that equilibrium hump. Now we're going to talk about chemical equilibrium, where we still have this stuff going on. We still have rates of reaction. We still have Ks, but now we're going to have a different K, and a Kc, a Kp, a Q, a Qp, a Qc, lots of different variables. Okay, this is where we get into starting with all the Ks and the Qs and the Ns and different things that are happening. So you got to kind of keep straight in your head which ones are which. All right, so with chemical equilibrium, we are talking about a forward reaction and a reverse reaction simultaneously occurring, eventually until they reach equilibrium. Both the products and the reactants reach an equilibrium, and then looking at the concentrations. Okay, so when we talk about these reactions, we're talking about reversible reactions, so we're always going to talk about the double arrow now. So we have our our reactants, our products, and we're going to have a K1, which is KF, K forward reaction, the K for the forward reaction, and then either K2, you will also see it as K prime, you will also see it as K reverse. They all mean the same thing. Okay, there's no difference between them. So that's going to be the reverse. And K2 is the invert of K1. So at equilibrium, the forward reaction is equal to the inverse of the reverse reaction. All right. So when you look at these, and what we're looking at is product and reactant reformation, product formation and reactant reformation, eventually reaching the same rate. Not necessarily the same concentration, but the same rate, okay? So when we look at equilibrium and we look at what's happening, over a certain amount of time, the forward reaction is going to go and form some products. The reverse of those products reforming back into reactants, that's going to be occurring simultaneously. When the rate of those two things are the same, we're at equilibrium. That doesn't mean the concentrations are going to be the same. We're going to have to take into account things like the coefficients. So if I have, you know, a coefficient of 1 for a product and a coefficient of 2 for a reactant, that means the reactant is going to be forming product twice as fast as the product is going to be going back and reforming that reactant, okay? So when we look at this, we always write the double arrow. You know you're dealing with equilibrium when you see that double arrow. Anything that has to do with the double arrow means we're going to be talking about what changes we can make to it, what disruptions in the system are, you know, what's going to make changes there, how that's going to happen. You see that double arrow, you immediately need to think about equilibrium and your equilibrium types of problems. So your equilibrium constant, K, capital K, or lowercase k, has the same rate law. Each K has the same rate law, what we've already done. So your rate equals K times the concentration of whatever it is. So in the forward reaction, your rate law is going to be this. Rate equals the K forward times the concentration of the reactant, all right? The reverse reaction, flipping it and going backwards. Now, I personally, I know your book likes to do this a lot, and you're going to see this in a lot of problems, and the reason I don't like it is because it's going to confuse you. What they will often do to show the reverse reaction is they will literally just flip the whole thing, right? So if you're looking here, you got N2O4 on the left, it's going to the right side. Here you have N2O4 on the product side. That's okay because it's the reverse reaction. What I personally like to do, which just makes life easier, it's not coming up. Come up. Where's my black pen? If we had N2O4 reverse reaction 2NO2 like that, right? Oh, can't see it. Sorry, guys. So if that's your reverse reaction, what I like to do is say this. Here's the forward reaction, right? That's the forward, so it's KF. And then for the reverse, I'm just going to keep it the same. And then just reverse my arrow. Because you're not going to see it split up. Your book will just take this one and flip it just like you saw. Okay? So you have to be careful of that, especially when you're working problems, because you're gonna walk through it and you're gonna be like, wait, why are they doing this? Why are they multiplying by this coefficient? What's happening? It's because really it's the reverse reaction that they've actually flipped, but visually it's more difficult to see. Okay? So just be careful with those and really pay attention to what is on what side so you know if you're talking about forward or reverse. Okay, so at equilibrium, we said the rates are equal. Not necessarily the concentration, but the rates. So if we have one rate equaling another rate, we can simply say this, okay? If you just substitute in, what you get is that the equilibrium constant is going to be equal to the products over the reactants, and the products over the reactants are going to be taken to their coefficient from the balanced chemical equation. Okay? So a more simplistic way to write this is K is going to be equal to the concentration of the products taken to their coefficients over the concentration of the reactants taken to their coefficient. Okay? You need to know that like you know how to add 2 plus 2. From here on out, we're going to see lots of product over reactant. Sorry, can you see? It's products, concentration of the products taken to the coefficient over concentration of the reactants taken to the coefficient. Okay? So almost everything, whether it's concentration, whether it's pressure, whether it's whatever it is, you're going to see from here on out a lot of product over reactant. So this is actually K subscript C because we're talking about concentration of the products and the reactants. Eventually we're going to talk about the pressure and it's going to be K subscript P so we can differentiate, right? But it's still going to be products over reactants. So if we talked about it this way, generically, Kc, K for concentration, is going to be products, again, taken to the coefficient of the balanced chemical equation over the reactants, all multiplied together. Everything is multiplied together, not added together. So the concentration of C taken to its power times D to its power, whole thing over A, concentration of A to its power times B to its power. Okay, yes?
So does the K stand for concentration or does it C?
K is the equilibrium constant. C is concentration. So for pressure, when we have pressures, it'll be Kp, which will be the equilibrium constant for pressures. Okay? And again, it's just a way to differentiate what kind of problems we're working. That's really all it's for. There you go, Kp. We use parentheses for pressure, not brackets. Brackets are to indicate as a kind of universal that we're talking about concentration. Parentheses indicate kind of as a universal that we're talking about pressures. So same thing, products over reactants, and we'll see this with partial pressures. Okay, several gases in a container that are mixing, for example. We'll see it there. We can relate Kc and Kp. There's an equation for that, but we'll get there. Questions about this so far? Pretty straightforward. We're on equation number 2, and it's literally almost the same thing. Okay? All right. Now, the reason we can relate concentration and pressure is literally the ideal gas law. We know PV equals nRT. That's ideal gas law, right? So when we rearrange all of this and we really kind of see what's going on, we can take into account the pressures, just solve basically for pressure. The volume is assumed a constant because we're talking about generally a closed container where the system is reacting and something's happening. And when we go down and through the math, your book goes through the step-by-step of how we can get to this. What we're going to end up relating is Kp equals Kc times RT from the ideal gas law taken to the change in N. N are the coefficients of the balanced chemical equation. So all I'm looking at is products minus reactants. Okay, for example, if I had, if I had an equation, a generic equation, I don't know what, hold on, I'm trying to fix integrity. It's not working, there we go. Okay, so if I had, I don't know, this is not a reversible reaction. I'm just totally making this up. Okay, so if I had that reaction, okay, and I was trying to figure out delta N, first of all, these are all aqueous. States are going to matter while we're doing this. Those are all AQs. Anything solid, we ignore. We always ignore solid because their concentrations don't change. All right, so we ignore the solid states. So if I were trying to find delta N, it's literally going to be the coefficients of the products minus the coefficients of the reactants. So what does that mean? Well, I got an understood 1 here and a 3 here. So it's going to be 4 total minus my reactants, understood 1 here, 3 here, 4 minus 4. Okay, so our delta N is equal to 0. Okay, yes?
On the notes here, it says moles of gaseous product minus moles of gaseous reactant.
Yep, the coefficients are moles. Okay, the coefficients of the balanced chemical equation are moles.
So we don't have to do like molar mass or anything?
Nope, you just take the numbers and just subtract them. Okay, so this is going to become important. Do you guys have it all written down? Can I?
Well, what is the delta N again?
The number of moles.
Subtracting that is just giving you the number of moles.
Yep, N is always moles. So what we're doing is products minus reactants. It's a factor by which we apply and involve the ideal gas law, okay, to try to relate Kc and Kp, okay? And we need moles to do that. And the R, the ideal gas law constant R that you're going to use is the 0.08221 because that's the only one with units that have an actual temperature of Kelvin in it. Okay, the other one is joules per mole. So you need your temperatures in Kelvin when you're looking at this. Okay, I don't want to look at that. So when we talk about K, we talk about it in terms of looking at its numerical value and being able to discuss it or talk about it in a way that makes sense. What does it mean for the purpose of the reactions? So here, there's a lot of little things you can memorize. If it's a really large K, and by large we mean greater than 1, then it's going to favor the forward reaction. The forward reaction is going to be more spontaneous and more favorable than the reverse reaction. And that's the direction in which it will proceed. If K is way less than 1, super small, and by super small we mean maybe anything smaller than times 10 to the negative 4, okay? What we're gonna see is it favors the reactants. So the reaction will proceed to the left more favorably than not. But if you think about that mathematically, if we go back to the equation here, this generic equation, if I have a really large number for the product side, that's going to give me a really large number greater than 1, just like fractional wise. Yes?
What is the significance of having 2 greater than or less than sign rather than this one?
They're saying a lot. Like, it's not just, oh, it's greater than. It's like way greater than. Because as close to 1 as you get is at equilibrium.
So there will never be an instance where it will be significantly more or significantly less.
When they do more than 1 greater than or equal, greater than or less than sign, it's because there absolutely will be almost every incidence where it's really, really big or really, really small. Okay? Think about it this way. Just think about if you plugged and chugged numbers in here, right? If I have 2 over 1 versus 100 over 1, right? The higher the concentration of the products, the larger number K is going to be, just mathematically speaking. In a fractional portion, if I reverse that and say, well, I have 1 over 2 versus 1 over 100, the larger the number on the bottom, the smaller my total value is. You agree? I mean, that's just the way fractions work, right? So based on how big or small K is, we can determine what has the most things present. Is it a really super small number and there's a lot of reactants? If so, the reaction towards the reactants, the reverse reaction, is favored. If it's a really, really large number, greater than 1, not a fractional piece, then the reaction in the forward product direction is going to be what's favored. So you kind of got to, if you can kind of wrap your head around it mathematically speaking, you'll remember it much easier, knowing always that it's products over reactants. Okay? So when we're almost equal to each other, like if equal to 1, we're at equilibrium. As close as you can get to 1, you're at equilibrium. So when we look here and we say, okay, so the products over reactants here, for whatever values they were, they just told you what the answer was. They told you it was 0.0212. If we look at the reverse of this, they've literally gone and just flipped it, and now they're doing the reverse of it. You're getting a really large number, okay? So what that tells you is the reverse reaction is what's favorable in this case, okay? The formation or the reformation of N2O4 is what's favored. The bigger the number, the larger, it's going to go towards that side, all right? Now, because they flipped it, you might want to say, oh, well, it's going to go to the product side. Well, technically, yeah, but really this is what the original was. Okay, this is why I don't like writing it this way and just flipping it. Because really what this whole thing is telling you is the reactant side going to the left is what's favored and going to happen most spontaneously. Okay? So, when you look at this, and we just look at this forward reaction here, well, this reaction as written, they tell you the Kc of this over this is this value right here. If you go back and you look at it flipped, which is, did they flip that one? Yes, they did. When you look at it flipped, a couple of things are happening here. First of all, they're multiplying it by a multiplier, if you notice that. Look at the coefficients. So 1, 2, 2, 4. They just multiplied everything times 2. When you multiply the whole equation by a multiplier, when you increase the concentration, Whatever that multiplier is also the multiplier for K. So when that happens, and sometimes you're going to have to multiply by something, either a whole number or a fraction. When you multiply, you have to do it to your rate also. Okay? And there are reasons to do that. You'll see as we go further and we work on problems, you're going to see there are times when they're giving us all the information about the forward reaction and are asking us questions about the reverse reaction. In that case, when it's the reverse reaction, we often have to, or it might be a variation of the problem. We might have to multiply everything, say, by 1/2. So for example, if this was our original and they asked us about this, we'd have to use the original information. We'd have to manipulate this so it agreed with this equation right here. But how will you do that? Well, we'd have to multiply everything by 1/2. And if they were talking about the reverse reaction here, we would multiply, take it to the power of 1/2, but then use the inverse of whatever the rate is. Okay, we're going to work on those problems. But so you're going to have to manipulate these problems. You just have to remember whatever you do to it, you have to do to the rate also, the rate that's given. Okay, the reverse rate is the inverse of the forward rate. And anything we multiply by, be it a fraction or a whole number, we have to take the rate to that power as well. You have to, don't forget to do that, because otherwise you'll get all confused. I want to find, hold on. I'm going to pull up my other PowerPoint. I just want to look at a couple of these with you guys. Okay, so if we look more into this, and we talk about, the forward reaction versus the reverse reaction. If you look at the K forward, right, C's and D's, remember, always products, A's and B's, always reactants. When we look at this is what we'd expect to see. And we'll get some numerical value based on whatever information we're given about that particular problem. And if we look at the reverse, we're literally doing the same. In the reverse reaction, what was the products formed kind of sort of becomes the reactants, because they're going to go ahead and form a new product, which originally were the reactants. So if you can kind of think of both the reactants and the products as both reactants and products, depending on if we're talking about the forward or reverse reaction, you can set these K values up very easily. And if you did the math on this, like let's say we had a number for it, we would find that the inverse for the reverse is the inverse for the forward. Okay, it's just a way of flip-flopping. So when we, I don't want to look at that. Let's just look at this. This is one of the problems I was going to do with you on Thursday. I'll just do it now.
Is there any way you can go back to that slide you were just on for the precinct picture?
This one? I'm going to upload this PowerPoint after class, if you want to just be able to grab it there. Okay? You good? Okay. So when you look at this, and we talk about manipulating all this stuff and what's going on, what's happening, what you see here is just a regular chemical reaction. N2 plus 3H2 yields 2NH3, and it gives you some rate. The rate is given for you. Okay, K is given. Doesn't matter what the concentrations are. Now what they're doing is they've said, okay, I'm reversing this reaction. Here's some other reaction that's different, and they want to know what's the new equilibrium constant there. Okay, so yes, technically it's the reverse, but what you see has happened is here, this NH3 has a coefficient of 2. Here, it happens to have none. This already has been halved, right? So the first thing we're going to do is we're going to find K reverse. K reverse is the inverse of K forward. So literally 1 over 5.6 times 10 to the 5. That's going to be your first step in the what's the equilibrium constant for the reverse reaction, given what we're given. Now, you will see that this was halved from this. They actually did that manipulation. So whatever they did to it, you have to take your rate to the power of that. They halved this, so you have to take the inverse and take it to the half power. Make sense? Whatever you do to it, you gotta take it to the half power. What I don't want you to do is say, oh, well, this is 2 and this is 1, so they must have multiplied everything by 2 here. That clearly cannot be the case. Why? How do I know that? So so you don't try to take it to the power of 2. How do you know it's not the case that they multiplied the first one by 2? One very simple way of seeing it. I think you know, Rachel. Do you know? You're looking at me like you know.
Are you saying because it's half?
No, how do you know? How do you know the difference is how do you know they actually did half this, but they didn't multiply this by 2? I mean, because that's a 2 and that's a 1, so something happened. We know something happened, right, with the coefficients. How do we know it's they halved everything here, but not multiplied everything here by 2? Right, the other coefficients are 1 and 3. If they had multiplied everything by 2, we at least would have had a 2 in front of the one that has nothing, just the 1, right, the N2. There would have been at least a 2 in front of that also, but there's not. So that's how you know they halved everything, because we got this 3 over 2 here, right? That's half a 3. We got 1/2 here. That was a 1. That makes sense. Well, now my 2 is gone. It's an understood 1. That's how you know they halved everything. That's how you know you take your rate, your inverse rate, to the half power as opposed to the 2. You can't just look at what you're looking at, right? You can't just look at the NH3s. You got to look at the whole big picture. So once you do that and you do the math, you plug and chug, it's 1.3 times 10 to the minus 3. So look at the difference between the K values. Which is the favored reaction, the forward or the reverse?
Forward.
Why forward? How did you know that?
Larger.
It's significantly larger, and this is still considered pretty close to 1. It's still considered a pretty small K. Okay? I mean, small in that it's closer to 1 than we would look at to have the reverse reaction trump over the forward reaction. All right? The forward reaction is significantly larger than the smallness of the reverse reaction. Make sense? Okay. I hit the wrong thing. All right, so if you're looking at this, we're not gonna do it, but what are we gonna do? Okay, same type of problem. We have 2.2 times 10 to the 6 being our K, and something's happened with this reaction. It's the reverse reaction clearly, but what has changed about it?
Coefficients.
By how many?
2.
2. Everything was multiplied by 2. So what are the steps we're going to take to find the K for this? First step is what? Do what? Yeah, inverse. First step is inverse. And then we know everything was multiplied by 2, so we take it to the power of 2. So it would be 1 over 2.2 times 10 to the 6th, whole thing taken to the power of 2. Okay? That's how you work those problems. Okay, I also want to talk about this. I know we talked about the equation already a little bit, but this is our relationship between Kp and Kc. Kp is the exact same stuff as Kc. It's just using pressures instead of concentration. Mathematically the same equations, just pressure instead of concentration, okay? Now, if we want to relate Kp and Kc, maybe they give you pressures and are asking for Kc. You can do this equation right here. So we already talked about delta N being the coefficients of the products subtracted by the coefficients of the reactants, right? The only time Kp and Kc are equal is when delta N is equal to 0. Why? Because anything taken to the 0 power is 1. That whole term goes away, right? So if delta N is 0 right here, this whole term goes away. That means when the moles are equal, the moles of the products are equal to the moles of the reactants, Kc is equal to Kp. Okay, questions about that? No? We'll do these.
What is equal to 0? Delta what?
Delta N. Remember we subtracted the coefficients? Yeah, when that is equal to 0, that means the moles are equal. So that's Kc equals Kp, because that RT term goes.
For example, the first Meriwether example you did, that would hypothetically be
Kc equals Kp. Yes, that's exactly correct. Okay. All right, I've already said to you guys that we ignore solids in terms of solving for the equilibrium constants. We only look at gases and aqueous solutions, okay? The reason for that is because they're solids, the concentration really does stay the same. It might change form, but the concentration is what it is, okay? So if we look here, this is just an example where we have solid carbon, and some reaction occurs, and it gives us carbon dioxide plus carbon, solid carbon. So we have carbon monoxide, carbon dioxide, and solid carbon. The back and forth equilibrium. No matter what's happening, the solid carbon, whether it's in the forward or reverse reaction, it is all there in the same concentration. It's just a matter of it's changed, whether it's the forward or reverse reaction. So we ignore the solid state because that's moot to concentration changing, all right? Concentration will change to get to equilibrium, but the ones that really change are when the species change. So if I have gases, let's say I have N2, and it forms NO2, okay? N2 plus O2 yields NO2, or N2O3, depending on which one I'm talking about, right? So you have different entities of compounds that are present. That concentration changes as reactants are reacting and products are reversing. So we just memorize it and move on. We ignore the solids. So if we're looking here at this, the Kc for this reaction would simply be Kc equals the concentration of carbon dioxide taken to the first power, because we're ignoring the solid here and the solid here. Those just get ignored, okay? Makes it a little bit easier, in my opinion. If you go in your book, let me find the page. Go to page 651. What time is it? Okay. If you look on page 651 at the conceptual connection, they're looking at a bunch of equations there. Okay, so if you look at those equations, the question asks you, for which one of these does Kc equal Kp? So there's two things you have to look at here. What's the first one? First of all, when does Kc equal Kp? When delta N equals 0. Why? Because anything taken to the power of 0 is 1, right? So that term goes away. So you have to look at where is delta N equaling 0, and what's the second thing you need to look at to figure that out? The coefficients, right? So if you look at them, what's the answer? pull up. I'll pull up the e-text. You guys got to bring your books to class, especially this week and next week. 651, the conceptual connection. Yeah. Mm-hmm.
What's the question again?
So it's on page 651. It asks, for which one of these reactions is Kc equal to Kp? Well, hang on. I want to pull it up because not everybody has a textbook. You guys got to, especially for like the next 2 chapters, you got to bring your book to class every time. I don't care if it's a laptop. I don't care.
And you said solids don't count, right? You're norm?
You tell me, do we, in this case?
Yeah.
Okay. So what are we going to do now?
We're gonna take each coefficient, subtract them, and
Mhm.
then equals 0. That's your answer.
Yep. All right. So let me just pull it up right quick. No. It's taking forever to load, y'all.
Think that's what the answer is?
Hold on, I'm trying to just pull it up so people can see it who don't. I don't want to print this page. I don't know where that just printed to, but it printed somewhere. Does the e-text not have the conceptual connections?
I have it.
You do?
Right there. That's the question right there, right?
There it is. Okay, yep. It just looks way different. All right, so here it is. We're looking at a couple things. The first thing, delta n has got to equal 0. So if we had just said, okay, 3 minus 1, okay, that's not it. 3 minus 4, okay, well, that doesn't count. 5 minus 4, okay, well, none of them. But that's not necessarily true, because for the first one, we got to ignore that. And for the simple fact that we have to ignore that one, that automatically will tell us not the first one. Okay? All right, ignore that and ignore that. So now we got 1 minus 2. Nope, that doesn't count either. All right? Ignore this, ignore this. Hey, 3 minus 3. Bingo, got it. Okay? You have to pay attention both to the states and to what it is you're looking for. So in this particular question, when does Kp equal Kc? You had to know when that happens, when all the delta n's equal 0, because when the moles are equal, the pressures and concentrations are equal. And that should make sense to you. And you got to pay attention to what do we ignore, what do we not ignore, because solids don't matter, only in this case the aqueous or gaseous ones matter. Okay, make sense? All right. Now, we've already talked about solids. We're going to talk about liquids also. Liquids we ignore as well. For the same exact reason we ignore solids. Okay? So, what are the only 2 states we're going to be looking at when dealing with Kc and Kp? Aqueous and gas. Okay? All right, so here's just an example. A closed system initially containing 1.00 times 10 to the minus 3 molar hydrogen gas and 2.00 times 10 to the minus 3 molar iodine gas at 448 Celsius is allowed to reach equilibrium. Analysis of the equilibrium mixture shows that the concentration of HI is 1.87 times 10 to the minus 3 molar. Calculate Kc at 448 degrees for the reaction taking place, blah. That's a lot. But this is what your problems are going to look like. Okay? One of the things we're going to focus on this Thursday and next Thursday are ice tables. Okay? So your ice tables we're going to use. But when you look at this, let's just get it written down and we're going to look at it a different way.
So is this where we use the ideal gas law equation? Or no?
You're gonna see. You're gonna see. So, do I don't even know if this is gonna work. Okay. Okay, let me just do this. Actually, you know what? I do have it pretty well set up. Okay. All right. So, I don't know why I went back over there. All right. So, when we look at this, I probably should have written the equation up here in this box, but I didn't. So, remember, it was H2 plus I2, reverse arrow, 2HI, right? Okay. So, when we look at this, this is our setup for an ICE table. ICE tables for the rest of this chapter are going to be a necessary evil that you're going to come to hate, but are super easy and make your life easy. So all that big, huge, jumbled up words of craziness that look like a really complicated problem, I'm putting into a chart format. So what I've got is my initial concentration, whatever it's going to change, and my what's at equilibrium. This is what we know. Initially, to begin with, we have this molarity of I2, this molarity, of H2, and this molarity of I2. And no product form yet, because we're talking about initial before any reaction, okay? They also told us that at equilibrium, this is how much HI was formed. So what that means is it increased by 1.87 times 10 to the minus 3. That also means these decreased by some amount, okay? I totally wrote the wrong number down, I think. Okay. I know, okay, never mind. So I want you to look at this as kind of like the second change here is 2 lines. So first I said, all right, so this increased by 2x, right, some amount, times 2 because its coefficient was 2. So these decreased by x. So if I take this number and I divide 1.87 times 10 to the minus 3, if I divide that by 2, that's 9.35 times 10 to the minus 4. Okay? So it changed by x amount, both of them did. The HI changed by 2x. Why? Because of the balanced chemical equation. So now we can very easily say, okay, this minus this gives you this, and this minus this gives you this. So at equilibrium, we have the concentrations for the reactants and the product. Okay, the product was given to us. We had to solve for the reactants. Okay, make sense? All right, now can we find the equilibrium constant K for this reaction at equilibrium? Of course we can. How? Kc equals products over reactants taken to its power. So Hi squared over H2 times I2, 1.87 times 10 to the minus 3 squared over 6.5 times 10 to the minus 5 times 1.065 times 10 to the minus 3.
Can you go back to the original slide?
Yes. This one? This one?
Right. My question is going from that question, how did you know to do that, the whole table that you have in the next PowerPoint?
Well, because from here on out, all we're doing is ice tables for the rest of this chapter. But the reason we do that is because what it allows us to do, and actually, let me do this. Let me make one change here. I'm just going to copy this. Or maybe I'm not. When we look at this and we say, okay, they gave us the reaction. They gave us reactant concentrations, just reactant concentrations, but then a product concentration at equilibrium, ice table. Always, every time. If it's at equilibrium or find equilibrium or something about equilibrium, ice table, because eventually you're going to use Kc or Kp. Okay? So typically, well, let me do it. Okay, I was going to copy this and put it here. Let's do another one.
Why is it called an ice table?
Initial change equilibrium, ice. Okay, so let me,
You said we use an ice table immediately when we are looking for the,
anytime you see equilibrium, ice table. Okay, that's your clue. All right, so let me just write this down. Can somebody just give me a time hack, please? Thank you. Let's start writing. Okay, this is going to be a very, very common problem you're going to see over and over and over again. Okay, so here you got a reaction given to you, concentrations given to you, and immediately you see equilibrium concentrations, ice table. Okay, you set it up in the table, and for those of you, if you want to follow in your book, I'm doing the example on page 658. Okay, so we're going to ignore Q because we're not doing Q today. We're doing Q tomorrow, next Tuesday. But just finding the equilibrium concentrations, we're just going to set it up. And we'll work through the actual answer of this more as we continue on with Q and then the X of small approximation and all that, which is the second half of chapter 15, which I'm doing next time. Okay. So what we would do is we would look at this and we would say, okay, I'm going to set up my ice table. The initial was given, and none of the product, okay? The change is going to be N2 changes by some amount X, we don't know. O2 changes by some amount X, we don't know. And 2NO changes by 2X. Everybody with me so far?
No, can you say all that again?
Sure. So the concentration of the reactants is going to decrease by X, by some amount. We don't know what that amount is. We're going to have to solve for it. Okay? The product is going to increase by 2X, whatever that amount is. And we don't know what that is because, again, we have to solve for X first. We're just not there yet.
And you know it's 2 because of that coefficient?
Yep, because of the coefficient from the balanced chemical equation. If there was a 3 in front of N2, I would have put minus 3X. Okay? Whatever the coefficient is in front of each reactant, that's what you multiply your X by. That's the change that occurs. Okay? Make sense?
so in front of that, X is an imaginary one.
I didn't hear what you said.
In front of those negative X's, those are imaginary ones?
Yes.
The ones as well? Okay.
The ones that are understood that we know are there because we're lazy and don't write them.
I just
Yep.
didn't know if that was something you had to do, the negative X.
If you want to put a 1 there to kind of keep it straight in your head, you're welcome to. When ones I just often don't write. Okay? Daniel, you have a question? I thought you had your hand up. Oh, okay. I just saw it over here. Okay. All right. So at equilibrium, what that means is that these concentrations are going to be 0.200 minus X, 0.200 minus X, and just 2X. Okay? That is the value of the concentration of each thing at equilibrium so far. Okay? Now, if I wanted to solve for x, I can still solve for x. I know I can because look, they gave me a KC. Right? So I can say KC equals 2x squared, right, over 0.200 minus x squared,
What squared?
because that times that is that squared,
I got that one, why the 2? Why 2x squared?
because the coefficient is 2. You still have to take, the rule is you take whatever it is to the coefficient that is its power. Remember, products over reactants, right? I know it looks like there's a lot of 2's there, but yeah, yes.
Well, quick question, since they're being divided, wouldn't they just cancel out anyways?
No, because you get a quadratic. We're going to do something else though. You'll see. Okay. All right. So now what we're going to do is we're going to change this up again and say, all right, we were given KC, right? That was our value for KC. And I'm just going to square root the whole thing. Okay. If I square root both sides, I get rid of my squares, yeah? Okay. So now can we solve for x more easily? Yes, much more easily. So, is it 0.1? Yeah, it is. Okay. All right, so I just solved for x. Algebra. That's just solving for x, though. That's not telling me the concentrations at equilibrium. Now, I would have to take that x and go back and plug it into the 0.200 minus x and the 2 times x, right? That will give me the concentrations at equilibrium. So once I've solved for the x, then I can go back and plug it in to those values. Then that will give me the concentration. Okay? And it makes sense that you get a negative concentration here, right? Because it went down. Now, there are going to be times when we have to do the quadratic, and we can sometimes make the small as x approximation, et cetera, et cetera. We're just not there yet. We're going to do that next time. We're going to do a ton of problems like this on Thursday, like a ton, between the book, my worksheets, and some old tests, all right? So I'll have them set up for you. What I might do, if I have time before Thursday, what I might do is just like type them all out on a document and have you guys print them and bring them in so they're already like printed out, then you can just write right on them.
Please.
Okay? Well, that's a lot of work, and that's like a lot of work when I can just put it up on the board and you guys could write it all.
That's a lot of work too.
I already know this stuff. We don't have to do it at all. I'm just saying. Okay. But, you know, doing that I think would be a lot easier, and like at least as far as like saving time, right? So questions before we go? All right, I will see you guys Thursday. Oh, by the way, just a heads up, you guys are getting yelled at in lab. You're in big trouble.
Why?
because when I went to leave last Tuesday, I always walk around again and I check everything before I walk out the door. The waist was wide open, left open, with the cap not even in the hood. It was on the desk, you know, that little desk next to it. The sash was open, and I cleaned up and put away a ton of glassware in the back sinks.
Can you let us know when we get over it?
No, it's got to come back to me when I like get into lab on, you know, this afternoon.